Welcome to this first video of my playlist about the preparation of pyridines. Pyridines are the technically most relevant heterocycles and important solvents and intermediates for a wide range of products. This video is about the preparation of pyridines by cyclocondensation, which is how pyridines are prepared on a large scale. In part 6, I'll show you some cycloadditions and rearrangements that can also yield pyridines. But cyclocondensation is by far more flexible and less expensive. In the other videos of this playlist, we'll have a look at transformations of pyridines by substitution of hydrogen, for instance halogenations, acylations, alkylations, or aminations. I will not discuss the transformation of functional groups, or substitution of one functional group by another, such as aromatic nucleophilic substitutions or Heck reactions. These proceed like in nitrobenzenes and do not usually require any special conditions. I won't discuss either the chemistry of quinolines or other polycyclic pyridines. Quinolines are much more reactive than pyridines, and their chemistry can only rarely be extended to monocyclic pyridines. The last video of this playlist is about the chemistry of pyridine N-oxides. These are easy to prepare from pyridines and can also be readily reduced to pyridines again. N-oxides are more electron-rich than their parent pyridines and are sometimes better suited for the preparation of substituted pyridines. Pyridines are weakly basic electron-deficient heteroarenes with a similar reactivity as nitrobenzenes. Electrophilic aromatic substitution is difficult, while aromatic nucleophilic substitutions proceed readily, in particular of leaving groups at positions 2 and 4. Alkyl groups at these positions are much more acidic than toluene and undergo condensation reactions as readily as ketones or esters. Nucleophiles usually add to positions 2 and 4, while electrophiles tend to react with pyridines at positions 1 and 3, or at alkyl groups at positions 2 and 4. Halogenated pyridines can be metallated stoichiometrically with strong bases, such as LDA, and then functionalized with electrophiles. These reactions are sometimes highly regioselective, but this regioselectivity can be difficult to predict correctly. Not only the equilibrium pKa, but also the rate of deprotonation can have an impact on the outcome. A few words on the parent compound pyridine. This weak base is miscible with water and many organic compounds, and is thus an excellent solvent, also because of its low reactivity and convenient high boiling point and low melting point. Pyridine and many substituted pyridines readily penetrate the skin. Pyridine itself is not very toxic, but 3 and 4 aminopyridine and some halogenated pyridines are highly toxic. A number of deadly accidents have occurred where people got contaminated with such a substituted pyridine and didn't change clothes fast enough. Pyridine is the starting material for the herbicides paraquat and diquat, and for the biocides pyrithione and chlorpyrifos. The required chlorinated pyridine intermediates are prepared by radical chlorination of pyridine, as described in part 2 of this video playlist. Another important product is piperidine, prepared by hydrogenation of pyridine. A number of natural products are also pyridine derivatives, such as nicotine, nicotinic acid, pyridoxal, and NAD and its reduced form NADH. Pyridines can be prepared by cyclocondensation of a 1,5-dioxopentane with ammonia. A huge number of variations of such cyclocondensations have been reported. For the large-scale preparation of pyridine and simple alkyl pyridines, the dioxopentane is prepared by aldol condensation of low molecular weight aldehydes or ketones, for example as sketched here. Instead of aldehydes or ketones, synthetic equivalents such as enol ethers or acetals can also be used, as well as carboxylic acid derivatives. These reactions are run at high temperature, often in the gas phase, and if dihydropyridines are initially formed, these will aromatize spontaneously. Here I've sketched the formation of a dioxopentane by Michael addition of acetaldehyde to acrolein, the latter being formed from acetaldehyde and formaldehyde. Another possibility is condensation of a formic acid derivative with acetaldehyde to yield a 1,3-dicarbonyl compound. Aldol condensation with acetaldehyde would then yield a dioxopentene. 2 chloropyridines readily undergo aromatic nucleophilic substitution and are valuable intermediates. One strategy for their preparation is condensation of a 1,3-dicarbonyl compound with a substituted acetamide, followed by deoxychlorination of the intermediate pyridone with phosphorus oxychloride or phosgene. A more environmentally friendly strategy is often the cyclocondensation of an oxonitrile with hydrogen chloride, as shown here. The required oxonitriles can be prepared from nitriles and 1,3-dicarbonyl compounds, or from nitriles and aldehydes. I'll show you later some specific examples. This here is one possibility for the gas phase continuous technical production of pyridine. A mixture of formaldehyde, acetaldehyde and ammonia was passed over a catalyst at 450 degrees Celsius. Along with pyridine, a small amount of picolines were also formed. I've sketched here some potential precursors to the observed products. A number of simple alkyl pyridines are also prepared industrially by gas phase cyclocondensation. Picolines can be prepared from acetaldehyde alone and ammonia, and treatment of acrolein with ammonia at high temperature yields a mixture of pyridine and 3-picoline. Picolines are important starting materials for halogenated pyridines required for the manufacture of important crop protection agents. In part 2 you can find many examples of the halogenation of substituted pyridines. Treatment of acetone with ammonia at high temperature can yield 2,4,6-collidine, as shown here. Aromatization required elimination of a methyl anion, not a very good leaving group, but at 400 degrees Celsius even weird reactions can happen. Ethyl-methylpyridine is manufactured by liquid phase condensation of the trimer of acetaldehyde with ammonia. One industrial preparation of nicotinic acid is the oxidation and decarboxylation of this pyridine with nitric acid at high temperature. This oxidation proceeds more smoothly than the oxidation of 3-picoline. Let's now have a look at some more laboratory-friendly cyclocondensations. 3 ketoesters can be easily condensed with formaldehyde and then with ammonia to yield symmetric dihydropyridines, as shown here. Dehydrogenation to the final pyridine succeeded with nitric acid, but a number of other oxidants can also be used. Dihydropyridines are in fact good hydride donors and reducing agents. Thioketene acetals, like the starting material of this synthesis, are obtained from ketones, carbon disulfide and some electrophilic methylating reagent. Condensation with a ketone followed by treatment with ammonium acetate gave a good yield of a substituted pyridine. One problem of cyclocondensations is that mixtures of regioisomers can result and that the products often have too many unwanted substituents. Here, for instance, the remaining thiomethyl group had to be removed by nickel-catalyzed carbon-sulfur bond cleavage with the sodium borohydride. 1,5-dioxopentanes also result upon radical addition of chloral to alpha-beta unsaturated carbonyl compounds, as shown here. Yields are often better than in this specific example, but because of the low cost of the starting materials, fair yields can sometimes be acceptable. In this example, a substituted pyridine was prepared from acrolein and a synthetic equivalent of a 3-ketoester. This reaction probably proceeded by Michael addition and ethanolysis and decarboxylation of the isoxazolone and can probably be catalyzed by a broad range of acids and bases. This example is similar to the previous one. Here a ketone was made more acidic by bromination followed by conversion into a pyridinium salt. Michael addition to metacrolein followed by cyclocondensation with ammonium acetate and elimination of pyridine yielded the final product. Instead of alpha-beta unsaturated aldehydes, also acrylonitrile can be used to convert ketones into pyridines. Under the conditions shown here, no activation of the ketone was necessary. Instead of ketones, trichloroacetic acid derivatives or chloral can be added to acrylonitrile. Cyclization and deoxychlorination of the intermediate can yield chlorinated pyridines, as shown here. Enamines sometimes undergo 2+2 cycloadditions to electron-deficient alkenes, instead of the expected Michael addition. The resulting cyclobutanes are not stable though, and can be cleaved to the Michael addition product, for instance by treatment with acids, as in this example. Cyclization of the product to a pyridone was also achieved by treatment with a strong acid. Another strategy for preparing 5-oxonitriles is by Wiltzmeier formulation of crotononitriles, as shown here. Substituted pyridones or 2-chloropyridines can also be prepared from simple aliphatic nitriles and 1,3-dicarbonyl compounds. In this example, valeronitrile was converted into a pyridone by treatment with malonic acid dichloride, without any solvent or catalyst. Another electrophilic 1,3-dicarbonyl compound suitable for this kind of pyridine synthesis is the enone resulting from the trifluoroacetylation of vinyl ethers. Here, this enone was first treated with a metallated nitrile and then cyclized with hydrogen chloride. In this example, this same enone was condensed with an enamine. Cyclocondensation with ammonium acetate then yielded a trifluoromethylpyridine. These are important intermediates for a number of crop protection agents. The starting enamine in this example is a synthetic equivalent of malonic dialdehyde. This enamine is probably easier to handle than the highly reactive parent dialdehyde. Aminomethylation followed by condensation with cyanoacetamide yielded a pyridone, which was then converted into a 2-chloropyridine with phosphorus oxychloride. The starting enamine of the previous example was prepared by Wiltzmeier formulation of ethylvinyl ether and then treatment with dimethylamine. Substituted 3-hydroxypyridines can be tricky to make. One possibility is the cyclocondensation of an oxonitrile with an alpha amino acid derivative, as is sketched here. The starting 2,4-mylsuccinonitrile can be prepared by formulation of succinonitrile with ethyl formate. The 3-hydroxypyridine prepared in this example was used as an intermediate for the preparation of pyridoxine, a form of vitamin B6. 3-hydroxypyridines can also be prepared by heterodiels-Alder reaction of oxazoles, as discussed in part 6 of this playlist. Here are some further, mostly recent examples from 4 journals only. You can also find these references in the description of this video. The next video of this playlist is about the halogenation and nitration of pyridines by substitution of hydrogen. Some of these reactions are again mostly run on a large scale and under conditions difficult to replicate in the laboratory, but I've also included examples well suited for small-scale preparations. See you then!